Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. Now in this video, we're going to do a little more structural design. We're still using some aerodynamics in this video. In fact, we're using load distribution, but we're going to use that load distribution to try to figure out the attachment for the outer wing panel where it's going to attach to the central wing panel of the UWS-4 ultralight airplane. Now this is part 11C of the playlist for the aerodynamic design of the UWS-4, but since it also has structural design in it, I'm going to put it into the structural design playlist for the UWS-4 also. And just in case you're new to the channel, or at least new to this series, the UWS-4 is an ultralight airplane design that I'm working on. It's supposed to be, I won't say all aluminum, but mostly aluminum. At least that's the goal. We've gone through the aerodynamic design part of the airplane, and now we're going to use the aerodynamic design to design the structural part of the airplane. So that's where we're going to right now. And by the way, when I say ultralight airplane, I'm talking about ultralight airplane as defined by the United States Federal Aviation Regulations, Part 103. Let's get to it. As is tradition in this particular design series, let's briefly talk about what we did in the last video. Now, in the last video, we talked about the span-wise lift distribution on the wing when we deflect ailerons and we deflect flaps. If you haven't seen that video yet, I'll put a link up here in the upper right-hand corner that you can click on, and it'll take you to that video. For this video, though, we're not going to use the lift distributions with the ailerons or flaps deflected. We're actually going to use the lift distribution that we got from Part 11A. And again, if you haven't seen that video, I'll put a link up here in this corner also. Now, in the aerodynamic portions of the video we've done in the past, we talked a lot about a book by Dan Raymer, Simplified Aircraft Design for Homebuilders. Now, this video, we're not really using Dan's book, but we are using another book and another publication. We're using a portion of Flying on Your Own Wings by Hein. Now, I got a link down in the description for this video that will take you to the books page of the Ultralight Airplane Workshop. And in there, you'll find a link to Chris's book if you decide you'd like to take a look at it, or if you'd like to buy it. Oh, by the way, if you do buy it, the channel will get a small cut of the proceeds. Now, another publication we're using, and you can get it online, Military Handbook for Metallic Materials and Elements for Aerospace Vehicles. And in particular, we're using Chapter 3, which covers the 600 series of aluminum alloys. And then I want to do a disclaimer on this video. You probably shouldn't try to use this video directly for any structural analysis that you're going to do. I didn't use any specifics of any book to come up with these calculations. I did it on my own. And there were quite a few calculations. So there could easily be math errors in what I did. And I could have made some mental errors in thinking about the forces that are being applied. What I'm showing in this video isn't quite enough to design the spar of the airplane, which is what we're talking about here, the spar attachment point for the outer wing panel. There's more things that we need to actually consider, but I'm trying to make this video just a little bit simpler. And we're not going to just rely on analysis when we go to build and fly the spar. We're actually going to test it first. We're going to test it until it fails to make sure it really works. There's also quite a bit of math here, but I'm going to kind of gloss over the math part. I'm going to talk about what we're going to start with, what gets plugged into the equations, and I'm going to talk about the results from the equations. So you don't have to worry about getting too much involved in the math or getting bored by the math. Let's get to it. So let's go over real quick what we're going to determine in this video. The first thing is, where do we want that spar to be in the wing? Generally, you want it to be at or close to the thickest part of the airfoil. And as I said before, we're only going to worry about the attachment point. Now that attachment point is going to be about 3.5 inches from the center line of the wing, at least the lower attachment point. And I chose that for practical reasons. I want this plane to be able to fit into an 8-foot wide trailer when I've taken the outer wing panels off. Let me jump in here for a moment and explain a change to this video. When I did the first edit of this video, it turned out to be about 40 minutes long, and that's longer than I wanted. I tried to keep the videos from being over half an hour. So we're going to figure out the bolt size for this outer spar panel attach point. And I had intended to also include the cross-sectional area that spar caps near that bolt. What I'm going to do is remove the part about doing the cross-sectional area. I'll put in the analysis for doing that cross-sectional area and the rest of the spar, not just near that bolt, into another video, and I'll put that into the structural design playlist for the UWS-4 Ultralight. So as a little picture to show you where it is, right here is where we're talking about doing the spar attachment. Now the reason I'm not doing center section is it's a little more complicated. As you can see here, there's booms that attach out here at the end of that center section, and there's landing gear. So that's going to add more complexity. So we should start with something a little bit simpler first. So here's a simplified cutaway view of what the spar will maybe be in the future. So it's kind of a guess here on my part right now. So this light blue area is what the spar will look like, that we're going to worry about in this video. So this is the outer spar panel. This darker blue is half of the center wing panel. And right here where this dark blue and light blue touch, that's an attachment point for the spar. And again down here, this is an attachment point for the spar. So a boom would attach here, landing gear down here. I put some dotted lines where I think I might put some ribs. I'm not real positive about that. There's a split between the flaps and the ailerons about halfway out on this wing panel. So that's about right here. There's going to be a spar web in here to carry shear load. There's going to be an aileron hinge out here, an aileron hinge here, a flap hinge down here, and a flap hinge here. Now it will be on the rear spar, not on the main spar. The reason I'm showing that is that these ribs next to these hinges are going to carry the load up to the main spar. So later on, I need to know where those loads are that's going to carry aileron and flap loads up to the spar. So that's why I've mentioned those here and where they are. So the thing we need to know is the moment here, where we're going to do the attachment point, and the shear load, accumulated shear load here at the attachment point. Well, before we get too far into the spar design, we need to figure out where it's going to be. Now we want that spar to be as thick as we can get it, at least considering other practical issues. Now the reason we want it to be thick, and by thick I mean height here, the higher that we can make this spar, the less material and the smaller the bolt we'll need, because there will be less force out here. If we made a little short one, there would be a tremendous amount of force both in the spar caps and on the bolt. And that's because the height of this spar is a moment arm. And the longer we can make that moment arm, the less force we'll have. Now the particular airfoil we're talking about right now is the airfoil designed by one of my patrons, Keith. Keith, thank you for this airfoil. And right now we're calling it the UAK-01 180 31 33 286. Now this UAK means it's an Ultralight Aircraft Workshop airfoil, and it's designed by Keith. That's what the K is for. And it's Keith's first airfoil that we're using. This 180 means it's 18% thick. 18% of the chord would be the height, the maximum thickness. That occurs at 31% of the chord, back from the leading edge. The maximum camber is 3.3, and that happens at 28.6% of the chord, back from the leading edge. So that maximum thickness is this blue line that I drew here at 31% of the chord from the leading edge. Now typically it's recommended, at least in general, that your spar be put at 25% of the chord from the leading edge. And that would be this location right here. Now we certainly could do that. A lot of airfoils have their maximum thickness pretty close to that 25%. Now it's going to be really hard to see, but right here at 25%, this chord has a slope down, and then down here at the bottom, this chord has a slope up. Now one of the things I'd like to do, at least right now I'm thinking about doing it, is I want to use an angle aluminum extrusion for the spar cap. So if I do that, that spar cap will be flat here, but we have a curve to our airfoil. So if I rivet the aluminum skin down to the spar cap, we're going to have a flat spot here, and then it's going to come back up, and then it's going to reach the thick spot. So that's going to deform the airfoil. And same thing on the bottom. It would flatten out that airfoil right there where I would rivet the skin to the spar cap, and I really don't want to do that. So I'm going to go back here pretty close to the 31%. I think I'm going to pick about 30%. That way when I have that spar cap in here with the angle, when I rivet it down, it won't change the shape of the airfoil. And same on the bottom. It should not change the shape of the airfoil, at least not very much. So right now, that's where I'm planning on putting the spar for the UWS-4. I did some calculations to find out how deep that spar will be. That's taking my 18% thick airfoil, multiplying by the chord, that's 5.81 feet, and that gets us 11.06 inches. So that's not too bad. It's almost a foot high. So that's what I've drawn here. Now on the center section, we have the same thickness as we have on the outer panel. So you can see from the top of my spar that I've drawn here, kind of symbolically, down to the bottom, that's 11.06 inches. Now I didn't really draw this to scale. For example, I'm showing a center line here, and then I'm showing the bolts out here. Now this is actually from the center line out here where this bottom bolt is, that's 42 inches, so that's 3.5 feet. So there's going to be a bolt right here where this spar cap meets the outer spar cap. And then up here, there'll be another bolt. Now this outer panel has a 12-degree dihedral. And I came up with that when I was using X-Plane 11 to do some flight testing of this airplane in a simulator. And I found out that I didn't quite have enough lateral directional stability. And that was with a 5-degree dihedral. So I kept cranking up the dihedral until I felt comfortable with the way the plane behaved in X-Plane 11. And that became 12 degrees. So for now, that's what we're going to use. Now to get us going, I'm going to assume for now that the height of my spar cap is going to be 1 inch. And it's going to be a 1 inch extruded angle, which means the leg flat on the top will also be 1 inch. I'm going to assume my bolt is going to be in the middle of that 1 inch. So that means it's going to be 1/2 inch down from the top, and its bottom bolt 1/2 inch up from the bottom. That means the center distance from bolt to bolt will be 10.06 inches. Now it actually will be just a fraction bit more than that because of this 60-degree angle that this bolt is going to be in from here, but we're going to stick with 10.06 for now. So let's talk about the forces that are going to be applied to this bolt. Now this isn't actually going to be all the forces, it's just the forces I'm going to use in this video. So we have the moment force, so lift on the wing, lifting out here somewhere on the panel is going to create a moment. So there's going to be a compression force here on this bolt, or at least near the bolt for the spar cap, and then a tension force down here near this bolt. And then that lift is also going to be creating shear through the shear web. So these two bolts also have to carry the shear over into the center section. So those are the forces we have to deal with. Things we're not going to worry about just yet are the forces on the center section. We're only going to worry about on the outer section, so we have to worry about things like the kick force. Now something that's going to be important here before too long is that when we calculated our lift force, that is vertical, straight up and down, but we really need the normal force, and that's going to be normal to the axis of our spar. So we have to convert from this lift over to the normal force. Now there's another normal force, which is when you're looking at it in the chordwise direction. We're not going to be talking about that in this video, although it is important. I did a video recently that I put into a new playlist, which is a structural design playlist. It's more generalized structural design. And in that particular one, we used lift forces to calculate the shear and moment on a wing. Now, one thing we did not do in that video, because I was trying to keep it simple, is that we did not subtract the weight of the wing from our lift. That's something we can do, which is really nice because it makes our forces a little bit less. That's because the weight of the wing is not transferred to any other part of the airplane. So it does not contribute to shear and it does not contribute to moment. But in order to subtract that out, we need to have a guess at what that wing weight is going to be. And we haven't done that yet. Now there is another airplane out there that is all aluminum, what we can use as our first guess. And that's good enough for now because this is going to be an iterative process. Because once we get results from this iteration of our design, we can actually do some detailed design on the structure of the spar and then do more accurate estimations of what our spar weight's going to be and the wing skin weight, our aileron weight, our flaps weight, and then do another iteration. And we can close in on the actual real values that we're going to need. Now, I've actually built a Ultra Cruiser aluminum wing before, at least the outer panel of it. And if I remembered right, that weighed 35 pounds, although I could be misremembering. It's been, gosh, 15 years or so since I built that. Now, since my wingtip is going to be different than the one on the Ultra Cruiser, I'm assuming that wingtip was about 5 pounds, so the outer panel was about 30 pounds. What I want to do is get pounds per square foot, and then I can apply that to my wing because I know what the square footage of my wing is. Then I can estimate what my wing weight will be. So the Ultra Cruiser outer panel was 35 square feet, and so that gave me about 0.85 pounds per square feet for the Ultra Cruiser outer wing panel. Well, now that I have this number, and I know my outer wing panel square feet, I can subtract my outer panel wing weight from the shear calculations and moment calculations. Now you may have noticed that the shirt I'm wearing in this segment is a different color than the shirt in the last segment. And that's because I had an issue with the first recording that I did. but we'll get to that here in a moment. What we're looking at here is a graph of the shear on the outer wing panel of the UWS-4 ultralight airplane. The red line is the original one. We've actually seen this in a previous video. It's just that we included the whole wing. Here we're starting at 3.5 foot, where the outer panel connects to the center section and extends on out to the tip. And this blue line is supposed to represent the shear when we subtracted the weight of the wing. When I first looked at this graph, I thought, that doesn't look like a very big difference without consideration of the wing weight and shear minus the wing weight. But I had the get there itis syndrome. I wanted to get the video done, so I just ignored it and plowed on. Well, when I was editing the video, I looked at it again. I said, that can't be right. And at that point, I did something I should have done much earlier when I first saw this graph. I did a sanity check of the shear at the attachment point for the wing spar. And speaking of sanity checks, I think I'm going to do a video in the future, probably not too far future, of how to do sanity checks on various parts of the design. And the sanity check is a quick and dirty, really rough estimate of the value you expect to see. So if your detailed calculation is fairly close to your rough estimate, then you're probably right. So I'm going to save how to do the sanity check for this particular situation for that future video. But my sanity check said I'm way off on this shear value here at the attachment point. This blue line should have been quite a bit farther down. So then I started doing some digging and I figured out what I did wrong. In the spreadsheet, when I was calculating the weight of the wing, I forgot to apply our load factor of 3.8. So I was just subtracting the weight of the wing at 1G, and so that wasn't nearly enough. Well, that ended up impacting all of the rest of the calculations in the video, so I had to redo most of the video. But let's look at what it should have been. So here's what it should have been. So you can see it dropped from right in this area quite a bit farther down. Now let's say I hadn't caught this error. What would have been the consequences, at least for this specific situation? It would have meant that I would have built my spar just a little bit heavier than it needed to be. I'm guessing if you include both sides of the wing, it probably would have been maybe half a pound heavier, maybe not even that much. So it wouldn't have been a huge difference. Although that half a pound could be the difference between making the 254 pounds empty weight and not making it. So I'm glad I caught this error and corrected it, even though it made more work for me. So the shear weight here at this joint was, when I did it wrong, 600 pounds, and now it's 500 pounds. So we saved 100 pounds in shear weight here at that joint. So that's pretty good. And for the moment along the spar, again, red is not subtracting out the wing weight, and blue is subtracting out the wing weight. So we're going to use these values here, right here at the 3.5 foot span in our calculations for both moment and the shear. There's something to take into consideration here when we're doing fittings, and where that bolt is going to be going through our spars, that is a fitting. And we're going to use part 23.625 fitting factors. Now in previous videos we talked about safety factor. We're using a safety factor of 1.5. So we're trying to design our structure so that it can handle at least 50% more load than we expect to experience. And that's because we could have errors in materials, we could have errors in our building process, we could have errors in our calculations. So that gives us a little bit of margin for safety. But in fittings, FAR Part 23 suggests you add just a little bit more safety factor. And they want you to multiply your results by 1.15. if you're not going to go through and do testing to prove that your design can work with a safety factor of 1.5. Now this particular bolt that we're doing right now is going to be a removable bolt. In other words, the wing panel is removable, so that bolt will sometimes go in and out whenever we're transporting the airplane by trailer. So that bolt hole will get a little bit of use. It's aluminum there, so that'll be a little bit of wear. So I'd like to have a little bit more safety factor. So I'm going to go ahead and use this fitting factor, even though I'm going to be testing to prove the structure can actually work. Now, since I'm doing this proof testing, I wouldn't really need to do it. In fact, I wouldn't have to do it at all, since ultralights don't have to adhere to Part 23. It's just a useful guideline to help design and build a safe airplane. But I'm going to do it in there. It'll give me a little more comfort. Since we have the shear and moment at that bolt where the outer wing panel joins with the inner wing panel, we can now start designing. Now those bolts there at that joint have to carry the moment and the shear from the outer wing panel into the inner wing panel. Now we were just looking at the shear. That was 500 pounds. I'm going to assume that I can design the wing spar so that each of the bolts, there's going to be one bolt in the top spar cap and one bolt in the bottom spar cap. I'm going to assume each of those bolts can carry 1/2 of that shear. So for that, that's 255 pounds for each bolt. Now if you'll notice, if you add those two together, that's actually more than this 495 pounds. And that's because we have quite a bit of dihedral on the outer wing panel. So that shear is calculated using lift, and that lift is straight up and down. But that shear really needs to be calculated normal or perpendicular to the axis of this wing panel out here. Now we have a 12-degree dihedral on this outer wing panel. So what we need to do is convert that lift force, that vertical lift force, over 12 degrees to this normal force. And that's what this cosine of 12 degrees does underneath here. That increases by about 5 pounds the amount of shear that we have to carry. That's not too bad. And that's an increase of about 2.2%. So if we had a very small amount of dihedral, let's say 5-6%, it's probably not even worth considering. We probably could have left out here since it's such a small percentage, but I wanted to include it here for completeness. And we're going to do something very similar when we work on the tail. Now let's talk about the moment calculation. Now from the spreadsheet, at that 3.5 foot spot out on the wing, the moment is about 1,780 foot-pounds. Now I want to get that into a force that the bolt's going to carry. So I take that moment, divide by the arm. Now the arm is the distance between the top bolt and the bottom bolt in the spar, and that's 10 inches apart. Now I need to convert that 10 inches to feet, so 12 inches per foot. Then we divide that arm by our foot-pounds, and we include our little cosine for the normal, and we get 2,190 pounds of force on that bolt due to the moment. Now we need to add that moment force and the shear force together for each bolt. Oh, by the way, that moment force will be the same, this 2,191 on the top bolt and the bottom bolt. You don't divide it in half to share it between the bolts. Now, how do we combine the two together? Those two forces are 90 degrees to each other, so you can actually use the triangle rule to do this. So we square one force, add it to the square of the other force, take the square root of that, and that'll give us the total force, 2,205 pounds. Now we want to add in our safety factor of 1.5 and our fitting factor of 1.15. Once we do that, we have a force of 3,804 pounds. We're also going to want to know what the angle of this force is once we've combined them. So what direction is that combined force? We're going to need to know that direction later when we add more forces in. And we'll talk more about what those additional forces are later. But we do need to know what direction that force is acting. So again, back here to this picture, we have our shear force here, we have our moment force here. When we add these two together, this force here will be that resultant force. And so we need to know what direction that is. So I've chosen in this case to have it relative to the axis of our outer spar. Now you can see here I came up with 6.64 degrees. Well, at least for the forces on the bottom bolt. Now on the top bolt, it is in this direction here. And again, it's 6.64 degrees from the axis of our spar. And that's for the top bolt. But how did I come up with this 6.64? By adding this one and this one together. Well, actually, that's pretty easy to do. You take the ratio of the shear force to the moment force, and then you put that into a trigonometric function called arctangent. You do that and we come up with 6.64 degrees. It's pretty simple. Now let's make sure that actually makes sense. Let's work backwards. We start with the 2205. Now that's before we added in our fitting factor. That's this value here, the value that we got right here. We'll take the cosine of that 664. And that comes up with 2190 and 2191. So we're really close, so that's good. So again, what I did is I took this force, I took the cosine of this angle, and it gave us this value here for the moment force, and it came out with the right number. So that's a way to do a sanity check, make sure we haven't made a mistake. So it came out pretty good. So here's a representation of the kind of bolt and spar attachment point I'm looking to do for the outer spar. So this out here would be our outer spar. It would actually only look like this out to about this point, and then there would be a flange out here to make it a little more stiff. And you could ignore these dimensions right here. We haven't figured that out yet. There would be this bolt going through here to attach our outer spar to our inner spar. We would have these thinner plates right here that come out to our bolt. So this is what it would look like at the top bolt and the bottom bolt. And we're looking at it from the top. And then there would be some fasteners in here to transfer force from this little plate in here to the inner spar. The thing I really wanted to show you here is our combined force that we just calculated is going to have to be transferred into the bolt, and the bolt is going to be transferred to these little plates right here. Now it's going to be transferred through shear on our bolt right in this area and right in this area. And each of these areas is going to take half of that force we just calculated. So half of it here and half of it here. So keep that in mind in what we're going to be talking about here in the next section. And by the way, this is called a double shear on this bolt. Well, we know what our double shear force on our bolt is going to be. This is 3804 pounds. So let's look at the double shear force on some standard Army Navy bolts, AN bolts. So I have AN 3, 4, and 5. So that's 3/16, 1/4, and 5/16 inches diameter. So we come over here to the double shear column, and the AN 3 can do 4,252. So that by itself is more than enough. And of course, the bigger the bolt, the more shear it can handle. So any of these three would work. Now I'm a little bit leery of using an AN 3. That's kind of small. But let's start with that and see what we learn. Oh, by the way, down here in the bottom, I also have the single shear and double shear for rivets. But of course, I want these outer panels to be removable, so we'll go with bolts. Well, now it's time to start thinking about the aluminum we're going to use. So what we need to figure out is what are the dimensions of the aluminum on this outer spar cap we're going to use that the bolt is going to run through. Now keep in mind, the strength value we want to use for this aluminum is the bearing area, because the bolt is going to use bearing strength on the aluminum, or vice versa. We already know one dimension now of this hole through this aluminum. We know that it's round and it's 3/16 inch in diameter. So now what we need to figure out is what alloy we want to use, and then how thick across here we want that spar cap to be. We're not going to worry about this inner side yet. We're only worried about the outer side. Now another thing we need to worry about or think about is the distance from the center of the hole out to the edge of our spar. The shorter that distance is, the less bearing that this aluminum can handle. The more likely it is to rip out, the less that distance is. Well, let's start with the 6061 T6 alloy. It's fairly easy to get. There are quite a few different extrusion dimensions and shapes we can get of this alloy. Another option is 2024 T4. It's a little bit stronger. It's a lot more expensive, about what, double the price sometimes? And it's a little harder to get a variety of shapes and dimensions in the 2024 T4 alloy. So right now, let's start with 6061. If we're not happy with it, we might go ahead and take a look at 2024 T4. So here are the various forces that this 6061 T6 alloy can have. So it's got an ultimate strength and a yield strength. Yield is the amount of force you can apply on it where it will start to deform, and then when you release that force, it can't go all the way back to its original shape. That's yield. Ultimate is where it completely tears apart. So we've got tensile ultimate, tensile yield. We have compression yield. We don't have compression ultimate. We have shear ultimate, but we don't have shear yield. And then we have bearing, ultimate yield. And we have two different edge to diameter ratios. Let's go back up and look at that. We have this 2 times the diameter of the ratio to the edge. That means from the center of the bolt out here to the edge of our aluminum, or this edge, it's going to be twice the diameter of the bolt. That's what this E equals 2 times D. So given that we have that dimension, how much force can this aluminum handle? So that's this value here. We also have when that E over D distance is 1.5. Now as you can see, it's easier to tear out at 1.5 than it is at 2. Now you might ask, should we use ultimate or yield values when we have both of those? Well, Chris Hein says something interesting in his Flying on Your Own Wings book. He recommends taking the ultimate, add the yield, and then divide by 2 and use that for your design numbers. So that's what I did over here for tensile and bearing for the E over D equals 2. So for tensile, using this equation and these numbers here, I come up with 34,500 pounds per square inch. And for the bearing load, it's 68,000 pounds per square inch. And by the way, this table over here came out of this document here, which is the one I mentioned up above, or this document right here. the metallic materials and elements for aerospace vehicle structures. So what we're interested in now for the bolts is these numbers down here, the bearing numbers. All right, now let's figure out how thick that spar cap has to be. So we're starting with a 3/16 inch diameter hole, 6061 T6 aluminum alloy. We're going to use Hein's method of adding the ultimate and yield strengths together for our bearing strength. That's 68,000 pounds per square inch. Now let's make sure our bar or angle or whatever we use is going to be wide enough. So using a diameter of 3/16, multiply that by 2. That gives us a center of our bolt hole to the edge of 3/8. Now we need to double that to go from the bolt hole center to the other edge. So that's going to be 3/4 of an inch. So this height here has to be 3/4 of an inch. Now let's use our force. We know that's 3,804 pounds. All right, now using all these numbers, here's our force. Here's one dimension, our diameter of our bolt. We divide by our yield strength, and that gives us our thickness. So it's 0.298 inches, or roughly 300 thousandths of an inch. Well, now that we know the minimum dimensions that we need for our thickness out here where the bolt goes through the spar cap, let's figure out what we can do with some of our standard dimensions for aluminum. So we need a thickness of 0.298 inches. Let's look at our picture over here. Here's where our 3/16 inch bolt would go through. So it's 3/8 out to the edges from the center of that hole. And we're talking height here at 3/4. I think I used the word width before. Now I'm going to assume that just a bit outboard of where our attachment is, we're going to use something similar to 1/8 inch thick aluminum angle. Now I'm going to remove the top flange for that angle here next to this hole. In fact, it would look a lot like this, where this would be the extruded angle, 1/8 inch thick. And then right here would be our attachment point where our bolt goes through. And then right in here, the angle where it would have this top flange removed would act a lot like a bar. And I'm going to have to attach some more thickness out here in order to get our total thickness. And remember, this is just for the bearing area for the hole. A little bit inboard from this, we don't need all that thickness, because then we only need the compression and tension strength of the aluminum, and that's going to be thinner. Now, one standard thickness that we can get for an aluminum sheet is 90 thousandths. So let's see, if we used one of those on each side of our little bar here, that would give us a total thickness of 0.305. So that's really, really close. So that would work. And we kind of get a little advantage because 6061 T6 aluminum sheet is about 10% stronger than extrusion. But we're not going to try to take advantage of that. We'll ignore it. Well, now let's consider using a bolt that is 1/4 inch diameter. We'll still use the 6061 T6 aluminum. So the only thing we need to change is down here from 3/16 to 1/4. Once we do that, we get a thickness we need for the spar of 0.2237 inches. So now let's consider what kind of standard thicknesses out here on this plate we can get. I still want to stick with the 1/8 inch thick center here. Oh, and by the way, our center to the edge thickness also has to be increased to 1/2 inch. So now we're a 1 inch high instead of 3/4 of an inch. So a standard thickness would be 0.063. So if we have one of those on each side, our total thickness is now 1/4 of an inch. Now I really like that because 1/4 of an inch is a standard thickness. So for now, let's consider using a 1/4 inch bolt. I really like that idea now. By having this outboard spar be an 1/8 inch and then 0.63 plates on each side for a total of 1/4 inch thick, that then gives us the option of having this inboard spar be made out of a single piece of 1/4 inch thickness. So I really like that idea. There's other things to include in here. I've referred briefly to them before, and specifically drag forces. Drag forces on this outer panel are going to try to pull the wing back. That will put tension loads on both of these bolts here. So it'll decrease compression loads up here on the top, but increase tension loads here on the bottom. So that's going to be an issue for this bottom bolt we need to at some point take into consideration. The airfoil also has a pitching moment. That's going to change the forces on these bolts also. So it's essentially going to change the shear forces up here. There'll be shear force on the rear spar and a shear force that has to be carried on these bolts up here due to that pitching moment. So that's going to change the forces on these bolts. Another thing that I mentioned before, we didn't change our lift vector to a normal vector. So let me show you that real quick. Now we talked about the normal vector versus lift vector when we were looking at the spar from the back. We also have it when we're looking at the chord direction of the wing. We have lift going straight up, but really we need to take into consideration normal force. In this case, it's normal to the chord line. So we really need to convert this lift over to a normal, and we didn't do that here in this video. And we haven't designed our shear web on the spar yet, and that could eventually cause some changes to our design. And then lastly, we're going to have to attach our ribs to our spar. That could cause some changes to our design. So there's still a lot left to do. I didn't want this video to get any longer than the rest of the videos, so we're going to cut it off here. So what are we going to do in the next video? We're finally going to look at the chord-wise lift distribution on the wing. Our A, D, G, and E conditions. And remember, that's our flight envelope conditions. For example, condition A is at our maneuvering speed with our load factor 3.8. Our D condition is at the dive speed, again with the load factor of 3.8. The E condition is with negative 1.5 Gs at our dive speed, and G is again at 1.5 but at our stall speed. Now I'm not sure we're going to do ailerons and flaps deflected. If we have enough time, I'll go ahead and do it. If not, we'll have to move it into another video. Well guys, thanks for watching. Until next time.